Which one's the pointer? Got it, okay. Okay, good morning, everybody. My name is Jared Mills. I'm here to talk about the first flight high contrast imaging instrument that we are planning to deliver to the Giant Magellan Telescope. I just got here this morning, so I haven't seen all the talks, but I'm sure that you've probably seen some version of these plots many times at this conference. Basically, all direct imagers are required to show something like this, right? So what I'm showing you here is all of the currently known exoplanets in two different plots. So I have mass versus luminosity normalized semi-major axis, so divided by the square root of L. This is sort of a spectral type independent astronomical unit. And then I have radius versus temperature over here. And all the gray dots are the confirmed exoplanets. This is just from the wonderful NextSea database. It's like a month old at this point, so I don't have, like, EPS Indy A isn't on there yet, at least not in terms of whether or not it's been characterized. So the colored points, you have the blue ones are our solar system, and then the green points are the planets that have transmission or emission spectroscopy, according to NextSea. And the purple ones are the direct imaging planets that have been characterized. And I'm using a very loose definition of characterized. It means we've collected a photon from that planet at some point. And the thing you should take away from this is that we're actually super bad at characterizing exoplanets. So, you know, JWST is starting to fill in this direction, and it's starting to help up here, but there's just all of these planets, and in particular, there's this really conspicuous gap right there, where we basically don't know anything about exoplanets. And I said we're bad at characterization, and direct imaging is even worse, because, like, we have to work way out here, far from the star. We have to use these young, hot planets that are, you know, very large radius. And so the context of this talk is that the ELTs are going to really fix this problem, but we have to do a lot of work to get there. And so this is the motivation for GMagAO-X. So we want to be able to measure, collect photons from these planets and measure something about their atmospheres in a way that isn't dependent on them being young or that they're having special orbits. And that kind of pushes us to wanting to work in reflected light, and I'll explain that in a little bit. And then we also have to get very close. So just for the nearby exoplanets that are interesting, that are in that gap, you sort of have 1 AU divided by the square root of L star, and you end up with something like 50 milliarc seconds or closer, which hopefully by now you've realized is super hard. So why reflected light, and why do you want to be in short wavelengths? And this is some work by Logan Pierce, who's here. You could scream, Logan, let everybody know who you are. You can talk to her about this work, but this is showing models of Proxima b and the atmosphere of Proxima b, and what you could learn from doing spectrophotometry on this. So you could just do a color magnitude diagram. Oh, this pointer is super weird. Color magnitude in the visible and near IR, and you could basically, the idea here is this is cloudy atmospheres, and this is various forms of mud, and you can tell the difference between a Proxima b with an atmosphere and a Proxima b with no atmosphere. And if you get a spectrum, you can look at all of these nice biosignature gases in the spectrum. But the key thing is here, we're working in the visible and near IR. The challenge here is that this is really hard. So you have to be super close to the star, and you have to work at high contrast. So this is lambda over D for the 25-meter telescope at 800 nanometers. And so we're talking about working inside sort of 10 lambda over D and getting down to at least 10 to the minus 7 sensitivity. You'd really like to be at 10 to the minus 8. So this is really hard. So the result here is that we want to be in the visible and near IR with high contrast imaging, and that's going to require extreme wavefront control. So hopefully everybody knows this fact, that diffraction limited imaging, when you're background limited, the sensitivity or the exposure time to signal to noise goes as d to the fourth. We tell our students that this is the one thing you should know about AO to pass a test on AO, is you have to be able to answer this question. And this comes from the fact that your telescope's bigger, so you're collecting more photons, and the PSF gets smaller, and so you have less background noise. And so these two things work together to make signal to noise go as d squared, which results in your exposure time going as d to the fourth. But the question is that true at 2 lambda over d? Is that true in the high contrast imaging context? Of course, I'm asking that, so the answer is probably no, right? And the problem is the spatially and temporally correlated noise that we call speckles. I'm sure you've heard lots about these by now, and that's this structure that you see in this coronagraphic image from GMagAO-X. Those blobs, those stick around, they don't go away, and that's what limits us. And so the ultimate answer is no, and it comes from this math. I sort of think this equation, which is a signal-to-noise ratio for speckle limited, is the whole reason this workshop exists. It's why direct imaging is hard. It's why we are struggling so much. And so what this is showing you is that the signal-to-noise is proportional to the number of photons from the planet, and that's just Poisson noise, photon noise, square root of n. And on the bottom you have the noise term, and that's the rest of the Poisson noise, and that's from the contrast. So here in this I sub h is the residual PSF contrast. And then over here you have this nasty beast, which is the speckle noise term. And you see that there's this extra I star, so there's more photons, there's another contrast, and there's this speckle lifetime problem. And so if you are in this regime that we call the quasi-static speckle regime, or anytime you're speckle limited, you end up with the speckle noise term being much bigger than the Poisson noise term, and you end up with this interesting equation. So you'll notice something in there. There are no photons. So all of a sudden, it doesn't matter how bright the star is. That means it doesn't matter how big your telescope is. All that matters is this speckle lifetime term, which is really setting the limits of your integration time. And then we get to this problem called the quasi-static speckle problem. And these are these long-lived speckles. This is why we do ADIs, why we do SDI, it's why we do PDI, it's why we have all these tricks to try to do high contrast imaging. And the problem is this noise source, the quasi-static speckles, sticks around. They have lifetimes of tens of minutes to hours. And when you're in this regime, all of a sudden what matters is your instrument design. It's optomechanics, which you can sort of think of as money. And you become really independent of telescope diameter. And this is a decades-old problem. If you go back and you read the literature from the early 2000s, you can detect this angst and despair setting in as high contrast imaging people started to realize this problem. And so what you need to do is get rid of the quasi-static speckles. So if you can do this, then all of a sudden you end up and you're limited by atmospheric speckles, which are really short-lived because it's the wind blowing across your telescope driving this noise source. So if you can get in this regime, then all of a sudden you're back to having a 1 over d squared contrast relationship, and your signal to noise is back to being d squared. So one thing to know here is that the answer is ultimately yes in high contrast imaging. Its sensitivity goes as d to the fourth, but it's actually for a subtly different reason than the isolated point source reason. I'll leave that as an exercise for the student to work it all out. So you do end up back with d squared, but the point is it's really hard. And so you need an extreme AO system, and you need really good wavefront control. And I think you've probably heard a little bit about GMagAO-X. This is the 2000 actuator extreme AO system that we take to the Magellan Clay telescope. This video shows us closing the loop, and you can see us adding more and more modes and the control radius zooming out. There's this little companion here. This is the star Pi Pup. That right there is the companion. All the other things you see there is junk from our DM surface. And so with this instrument, we've been working really hard to develop this wavefront control ability and this ability to get rid of quasi-static speckles. And I know you heard all about this from the man himself earlier this week. But just last April and May, or was it March and May? The runs run together at this point. We demonstrated on Sky for the first time this implicit electric field conjugation technique. And you can see Sebastian very cheerfully showing the speckles just go away. You see under his finger that it just gets fainter all of a sudden when he turns on the EFC. And you see us go from these residual quasi-static speckles to basically nothing. And then there's that fake 10 to the minus 4 fake planet that he injected in the data. This is extremely important that we are now moving towards making this something we do on Sky all the time, because this is the secret to getting the real efficiency, the real sensitivity of our telescopes in high contrast imaging. So the message here is that if you want to get to this d to the fourth scaling at 2 lambda over d, and you want to have this ultimate sensitivity that the ELTs promise, you need to work really hard. And you need this extreme AO capability. You need high STREL. STREL goes towards efficiency, but also stability and linearity. And this is especially true in the focal plane and in things like coronagraphic low order wavefront sensing. What we're finding with GMagAO-X is that if we're in bad seeing and the AO is not working really well, this stuff just doesn't work. So you have to have high strel, you have to have stability, and this is especially true in the visible. So what this is all pointing to, and this is actually getting to the rationale for the GMagAO-X design, is that you need a high actuator count DM. You need a lot of actuators to make this happen. So this is the Giant Magellan Telescope. This is a 25-meter telescope made out of 7 8.4-meter segments. And this movie is going to pause here in a second. Of course, it's going to look exactly like that if you fly a drone over it. What I want you to notice is that it's got these 7 segments, and just sort of freeze the pupil in your mind here, so that it's this petal-shaped thing with the central segment and the 6 segments around it. And this presents some unique challenges, but also some interesting opportunities. So for GMagAO-X, what we want to do is build a 21,000 actuator deformable mirror. This is something you cannot buy today. No one will sell you that. No one will even sign up to try to make it right now. There's people working on it, but our rationale here is we can actually figure out how to do this using technology you can buy today. And so the idea is you have that GMT pupil, and it just happens to be the same shape as a current telescope. And so we can use current deformable mirrors if we split it up. And so you can sort of follow this, this cartoon where the yellow lines are coming in from the telescope, and it hits this mirror here that's a 6-sided prism. And it's coated like a mirror, and it splits the light up into 7 different segments. The center one goes through a hole. And then the light comes back out, and then gets reassembled, and then goes into the coronagraph. And so by using 7 segments, each one with 3,000 actuators, we can make the equivalent of a 21,000 actuator DM. This is the actual design of that. It's affectionately known as the water wheel. It doesn't spin, but because it looks like, an old water wheel. And so there's that prism. You see the DMs here. Each one has 3,000 actuators. And then note here that there's this stage here with a fold mirror on it. You can see the light come in and bend off the fold mirror and hit the segment and then come back out. And that's really important because that's how we do alignment and segment phasing with this device. And this actually exists. So we've prototyped this in the lab at University of Arizona. These are former grad students, now Dr. Hedgelin and Dr. Kautz, aligning this thing for the first time. You can see that shiny hex prism there, and then you can see what it looks like. And if you look at this, you can actually see the GMT pupil imposed on it as we're testing it. And then what this does is it works in this test bed called the High Contrast Adaptive Optics Phasing Test Bed at the U of A. There it is sitting on that optical bench. We cut a hole in the wall and it goes into the GMagAO-X lab next door. And we ship GMagAO-X back and forth from the telescope, and when GMagAO-X is home, we do experiments with GMagAO-X pretending to be the AO system on the GMT. And so we basically built this GMT extreme AO simulator in the lab. And one of the big problems that we're dealing with is segment piston. At least we thought it was a big problem, or everyone used to say it was a big problem. And so the issue is that the GMT has these segments, and they want to get out of phase if you're not careful. And so what that means is that instead of all having the same perfect optical surface, let's say that you get out of shape by just 45 nanometers. So that just means that they're all a little bit at a different position, and so the OPD is a little bit different. And then behind your coronagraph, you end up with this, which is really bad, actually. That would kind of ruin the whole point of GMagAO-X. But with just 6 nanometers, you end up kind of there. This happens to be the spec for GMagAO-X. And so the goal of HCAT was to make sure that we knew how to deal with this and we could solve this problem. And so this is just showing one example of the results we're getting in the lab with GMagAO-X, or with HCAT and MagAO-X working together, showing us being able to be out of phase, which is when you start up the GMT every night, it'll look like this, and then you have to get it to here, which is sort of all of the PSFs are now aligned, and then you get all those segments in phase, and you end up with a nice GMT PSF. So the key takeaway here is that we actually have a DM. We know how to do this. We can build this 21,000 actuator DM that we need to do this extreme AO. This is, for the GMT, you would need a 182 by 182 actuator DM. This is the same actuator pitch as we get on GMagAO-X, and the nice thing about the MEMS is it gives us this 10 kilohertz response time, so we have a very fast system. And as I've emphasized several times, you can buy this today. This is basically a display piece. It's something that they broke at Boston Micro Machines and then gave to us. They slapped our logo on here for us. Because you can place a purchase order for this today, this is relatively low risk in terms of being able to build GMagAO-X. So that takes us to GMagAO-X, finally. So GMagAO-X is going to sit on what's called the Gregorian instrument rotator, which is down here below the primary mirror of the telescope. So this is a cutaway, but those are the 7 segments of the primary mirror. And it sits on this rotator, and that's what it's going to look like. So it's got this big metal frame holding a rotating barrel, some electronics racks, and we're building our own M3 mirror. It's an important thing to know is that in a high contrast imaging instrument, M3 is usually your biggest problem. So to solve that, we're going to build our own that we have control over and can make it a very nice mirror. So the science cases for this are, of course, reflected light imaging and the search for life. So the ultimate goal for GMagAO-X is to go characterize nearby terrestrial, potentially habitable planets and figure out if they've got life on them. We're also going to focus on characterizing young EGPs. This is sort of today's science, just better because it's on a bigger telescope. Planet formation at low mass and small separation, you can interpret that as H-alpha, looking for accreting protoplanets. It'll be really good at circumstellar disks. Also resolve stars, so we'll be able to resolve the surfaces of evolved stars and take spectrum of them, measuring things like turbulence in their atmospheres. And then solar system science should be really fun with GMagAO-X too. To answer the question about can we do this, well, we think we can. So these pink lines here are what we are planning as the sensitivity or contrast performance of GMagAO-X. So this is the 5 sigma post-process astrophysical flux ratio. So this is the sensitivity to planets that we expect to get. And we've defined our minimum useful spec as 4 lambda over D and 10 to the minus 7. And you can see right there you're getting into the sort of 20 planets that you would be able to characterize with GMagAO-X in reflected light. And our target, what we're actually trying to build the instrument to, is this line here, which goes into 2 lambda over D and gets down to 10 to the minus 8. And then the goal, which means we're going to keep working on this until we hit a showstopper, is really aggressive. That goes all the way into 1 lambda over D and goes down to 10 to the minus 9. Kind of an eye chart, but just this shows you the specifications for GMagAO-X. So the big thing is that we're going to work from at least R band to H band. We would like to get all the way down to 350, but there's some optics challenges with that. That gives us 5 milliarcsecond to 3 milliarcsecond resolution. We're planning a suite of spectrographs. We'll be able to do everything from sort of just standard 10% photometry all the way up to potentially as much as R of 100,000 spectroscopy. One caveat to that DM design is that it results in a very narrow field of view. So we're only going to actually cover about 3 arcseconds by 3 arcseconds. I only care about like 10 milliarcseconds, so this doesn't bother me, but this isn't going to cover all the science cases you would want to use the GMT for. So just to show you some of the fancy preliminary design stuff we've done. So one thing about that phasing problem that I described and trying to do a coronagraph is that, especially with 5 milliarcsecond spatial resolution, is that vibrations are killers. And so we're going to actually have GMagAO-X sitting on a floating optical table. Just like you go in a lab and you push on a table and it bounces up and down, GMagAO-X will do the same thing, except it's going to be under active height control. This doesn't seem that special until you realize that GMagAO-X doesn't have a Naismith platform. So there's no gravity invariant place to put this optical table. So we're building one. So this 2-level optical table sits inside this frame, and there's a bearing on the front and a bearing on the back. And the whole thing rotates. So if the GMT is pointed up, pointed at zenith, and you see that this barrel here is pointed up also, and then the GMT tips over, our barrel has to counter-rotate very precisely because we have this floating optical table that's sitting there sliding around on air, right? So if the telescope tips over and we don't tip over, we'll just slide right off the telescope. And so that has actually been, sort of a major part of our engineering effort is to keep that safe, and I'll show you some slides later. This is the optical design of GMagAO-X, just a very quick overview. So It's a 2-level optical table, so all of the AO system is on the lower bench. It comes off our tertiary and goes in through some coupling optics. This includes a fast steering mirror that is where we're going to do our primary vibration correction. There's a K-mirror and ADC. The K-mirror is for derotation so that we can do angular differential imaging. It's a woofer tweeter system, so we relay to the woofer, and then back in here we get to that parallel DM, the 21,000 actuator DM. And then it gets relayed to the upper level, which is where the coronagraph is. And this is where we feed the spectrographs and all of the science backends. I was hinting at this safety problem because we have this 10,000-pound instrument on a rotator, on a tipping telescope, on air, so it's sliding around. Also in a place that's prone to huge earthquakes. So we've had to spend a lot of time making sure that it won't just fall apart. And so we have things like this locking mechanism so we can lock the instrument down and it won't slide off the telescope. And it has to pass the survival level earthquake without exploding. And we've made sure that all of that stuff is good in our design. With any extreme AO system, the electronics and the computers are sort of a problem. We have these 2 large electronics racks that are going to ride along with GMagAO-X. Those are actually almost exclusively DM electronics. So the woofer is a 3,000 actuator DM, and then we actually have 8 MEMSs because we have the 7 segments for the high order DM, and we have another DM which is specifically to do coronagraphic non-common path aberrations, just like we do on MagAO-X. The other problem is with 21,000 actuators, you need the computer that can control them. We're basically going to be running an AI data center in the basement of the GMT to do this. So up on the telescope, we have the wavefront sensor detectors, the DMs, and then the drivers that are in those electronics racks, and then we have to ship all of that information from the wavefront sensors down to the basement to a bunch of computers, and we basically can't figure out how to do this with one computer. So we're building this distributed real-time computer. It's sort of hidden here, but there's GPUs right there. There's probably going to be like 30 GPUs involved in this if we use today's capabilities. And then you have to get all that back up to the telescope, and you have to do this whole loop. It's going to take about a millisecond, is the idea. So it's actually a pretty significant computing challenge, a lot of interesting algorithm development to do. Coronagraph design, this is just an example of one of the designs we've done. This is by Sebastian Havert, and this is the phase apodized pupil Leo coronagraph, which is our baseline. And you can see that we can dig a nice dark hole with the GMT pupil at 2 lambda over D and a 20% bandpass. We're also going to support PIA complex mass coronagraphs, which that's how we'll get into that 1 lambda over D and that super high contrast stuff. Key message from this is that the GMT aperture, even though it's that interesting petal shape and stuff, is not a challenge for coronography with all the modern techniques that we know about. In terms of performance, this is specifically for Proxima Cen, so this is a 7.5 magnitude star at 800 nanometers. This is raw contrast. This is limited by the atmosphere, assuming we've gotten rid of quasi-static speckles. The red curve is for predictive controller, and the blue curve is for a standard integrator controller. And this is contrast, and this is speckle lifetime. So one of the things, because we sort of realized that the key limiting thing here is this speckle lifetime problem, we've actually specified speckle lifetime as part of the GMagAO-X design. And the point of these plots is that with our current design and our control system design, we actually meet our specs so that we can achieve the sensitivity that we're predicting. Current status, so we've done conceptual design, and we just had preliminary design in February 2024. Thank you to our committee. I think there's at least 1 or 2 of you here right now. We have the full support of GMT. We're basically integrated into the project and going forward and planning to get ready for first light. We want to do final design review sort of late next year, and right now we have a schedule that closes for 2032 commissioning. And buying those MEMS segments is the long lead time. MEMS, you can't just place an order on Amazon for a 3,000 actuator MEMS and have it overnighted. Okay, so back to this problem we have where we're not very good at characterizing exoplanets. So remember I showed you this, and here's the punchline. With GMagAO-X, we'll fill in that gap. So these are all of the planets that GMagAO-X should be able to characterize if we meet all those performance goals. I want to emphasize something here. These are known planets, right? This isn't like based on a population model. This isn't like projecting things based on a blind survey. There are RA and DEC that we could point at right now. We know those planets are there. And all we need to do is go collect some photons so we can learn about what's going on in their atmospheres. So, in summary, I want you to understand that this D to the fourth advantage that we talk about with telescopes, and I'm being a little, the elephant in the room here is I'm proposing to do this on the smallest of the ELTs, but there's a good reason for that. And it's because it's really hard and you need that DM. You need to be able to do this. And the GMT design is actually sort of useful in terms of being able to do that. And this is how we're going to solve this problem that Astro 2020 laid out, which is go search these planets for life. We need your help. So we would love to grow our science team. So if you're interested in helping us develop these science cases and figure out how to do this, come talk to us. We're hiring postdocs at U of A. If there's undergrads listening, apply to be a grad student at U of A. And something else that we can all do is we need to make sure that the NSF makes the right decision on the US ELT program. So, use Twitter or Mastodon or whatever the cool kids are using and make this obvious that this is the right thing to do. So that's the end of my talk. I'll close here with this picture of some part of the GMagAO-X clown car at Clay and just thank our sponsors that have helped fund all this research. Thanks.
Thanks, Jared. Time for a couple questions. Let's do right here first.
Hi, Aniket Sanghi from Caltech. Thanks for the great talk. I was curious what sets the lower limit on the science wavelength that in the optical that GMagAO-X can work with?
Your question was what was the lowest wavelength?
Yes. Or you mentioned like 350 nanometers has challenges. So what are some of those challenges?
So the hard part is that the atmospheric dispersion starts to get really bad in the optical. So you know that the index of refraction versus wavelength is super steep as you go through the optical. And so it's actually designing things like the atmospheric dispersion correction and any refractive optics you have into getting a solution that covers that wide of a bandpass all the way from 350 to 1900 starts to get really hard. We can do it at 600, 450 makes the optical designers nervous, and 350 they start laughing at us. But I think there are solutions. It just depends on how much money and space we're going to devote to it.
Okay, thank you.
Akiba Bursch, NASA Goddard. This parallel DMs thing is super interesting. Could you talk a bit about the issues with implementing that on a different aperture that's more like lots of little segments, little hex segments?
Sure. So we've actually looked at this. Sebastian Haffert contacted Boston Micromachines and talked about this, because what you would want to do is build a MEMS that's in the hex segment format. So you could do it. It's just that if you did this with the TMT right now, you'd just be turning the TMT into the GMT by using circular apertures, which would be effective. You would do great work with that. But Boston Micromachines will sign up to wire up a MEMS in a hexagon for you. It's just an R&D project, and they are willing to look into it. So it's a possibility.
Thinking more for capitals.
Same thing, right? If you have a segment, if you have spiders, you already kind of have a naturally segmented telescope, so why not? And it's totally possible that you can buy a MEMS in a circle, you can buy a MEMS in a square. They've just never been asked before, can you make me a hexagon or a parallelogram, and they'll do it. So it's just an R&D effort, so it's definitely worth looking into. And you should talk to Sebastian, because he actually has done some real investigation of this. So.
All right, I don't think I want to cut more into the